Okay, I'm gonna start. I can't hear anything you're saying. Wait. Okay, you know what? Just mute yourself. Ask me questions in here if you need to. Are any people watching? Oh, 3 people are watching. That's impressive. There's 2 people watching. It's crazy. What is this? What are you telling me? Tell me in the chat fast what my voice is. Doubled. Oh, okay, 1 second. Mute me in the voice chat. I mean, my voice is muted in the voice chat. Why is my voice doubled? 1 second. Voice is muted in the voice chat. Why is my voice doubled? 1 second. No, it's not doubled. Are you insane? No, it's not doubled. This is fine. Okay, see, it's okay. Yeah, okay. Now I'll do the thing. What is this? Here's a test. Okay. First question. Okay, what factors can affect the rate of reaction? So the particle size of a solid reactant. Yes, the particle size can affect it because the smaller the particle size is, the higher the surface area of the reactants are. In which case, you'll have a faster rate of collisions, and more collisions happening. For number 2, concentration of reacting solution, that also affects rate of reaction, because if you have a higher concentration of molecules in the same amount of area, you're going to have more collisions as well. For number 3, yes, same phenomenon. If you're having increasing pressure of the gas, that means there's going to be more of the molecules in a smaller amount of area, a smaller amount of volume, which means that again you're going to have more collisions every second. So the correct answer is D. For number 3, copper catalyzed the reaction between zinc and dilute sulfuric acid. So in this scenario, why does copper affect the reaction? It's because the copper, acting as a catalyst, reduces the activation energy, and it basically decreases the activation energy. Yeah, so it decreases activation. It's just 3A, because that's what a catalyst does. The catalyst, if you're looking at like an enthalpy level diagram, just real quick, look at enthalpy reaction profile like this, and an enthalpy level diagram like that. The activation energy is the amount of energy, how high it needs to go. The catalyst reduces this amount and makes it go lower so that we don't have to go as high. Any other changes will not affect the activation energy. The catalyst is the only thing that affects activation energy because it creates an alternate reaction pathway. Oh, I don't know what that is. Okay, that's fine. Let's keep going. Question number 4, what is the correct unit for expressing the rate of reaction? It's moles per decimeter cubed per second, because that's like molarity is M, the capital M over S, and moles decimeter cubed, moles decimeter to power -3 is concentration over second, so it's S to -1. Which is not affected by an increase in temperature. For this one, the rate of reaction is affected by the increase in temperature. So if you increase the temperature, yes, you do get an increase in the rate of reaction. But for then you have collision frequency, which obviously also increases the rate of not affected by an increase in temperature. An increase in temperature will affect the collision frequency because you're going to have a higher kinetic energy over on average, because that's what temperature means. And in that sense, you're going to have faster moving particles that are like more frantic and chaotic, which results in a higher collision frequency. For C, collision geometry, that does not being affected by temperature, because it depends on the angles that it's been hitting, and in which case collision geometry is the correct answer. And the reason D is not the correct answer is because the percent of molecules with E greater than activation energy EA is much larger. So I think one way to look at that is to look at the Boltzmann distribution. If this is your Boltzmann distribution with energy on this side, how high if each particle, and it looks like this, and you have the activation energy over there, there's this many particles over here. What the temperature ends up doing is that it shifts the Boltzmann curve more like that, which means now there's an increased number of particles in that region to the right of the activation energy. So yeah, that's how that works. Yeah, just give me 1 second. Okay, I'm back. Are people still watching? Wow, only 2 people. This is amazing. This is so amazing. Question 6. Which piece of equipment could not be used in an experiment to measure the rate of this reaction? I could go through why all of these could be used, but really you can't use the gas syringe at all, because there's no gas in this entire experiment. You have 2 aqueous solutions and then a bunch of other aqueous solutions. You're not going to get any gases anyways, so you can't expect any gases to come out of this thing. So at the end of the day, you can't use a gas syringe. 7 is skipped, I don't know what that's up with that. 8, a piece of zinc was added to aqueous nitric acid, and the volume of hydrogen gas produced was measured every minute. Results are plotted on the graph below. Which graph would you expecting the same mass of powdered zinc was added to nitric acid with the same concentration? Over here, when you powder the zinc, that's the key part over here, a piece, and here's the powder. So a powder means that you have a higher surface area because you have a lot more particles. And the fact that you have a higher surface area means that the reaction rate is increased significantly, which means that the same maximum peak will be reached because it's the exact same mass. However, it'll be a lot faster, and that's why it's going to be question number A, option number A. 10. The table gives rate data for the reaction in a suitable solvent. So here's what it looks like, and here's what the data is. So we can go through each one of whether it's C is correct. So the rate expression is rate is equal to K. And this is the concentration of one reactant, concentration of the other reactant. Both of them are order 1 in this rate expression. And we can check what order they are. So let's look at the difference between experiment number 1 and experiment. Open. Difference between experiment number 1 and experiment number 3 over here. So if you look from 1 to 3, you have a double in the the hydroxide concentration. However, you have no change in the rate of reaction, which means that for the OH order is equal to 0, which means this cannot be true, because this says the order of OH as plus 1. Then the rate increases by a factor of 4 when the OH is doubled. Again, that implies it's order 2. But the OH has absolutely no effect on the actual reaction, and how much OH doesn't affect the rate of reaction. So I don't know what SN1 mechanism means, but I'm pretty sure that CH9Br is a primary halogeno alkane, because what that basically means is that it's an organic compound with some halogen attached to it. So this is the only possible option. However, this isn't in our like thing, like our unit. So I don't know like whether or not this is like you should worry about this, but yeah, I don't think this is like that important because it's not like something we've studied. Consider the following proposed two-step reaction mechanism at temperature T. Okay, which statement is correct? The overall reaction is NO2 plus CO plus carbon monoxide gas. It gives you nitrous oxide plus carbon dioxide. What I can do over here is cancel out stuff. So I know there's an NO over here, there's an NO3 over here and NO3 over here. So that cancels with that when I add them up. The 2 NO2, there's nothing else that really cancels. There's one that cancels here, the NO2 will cancel with that one and give an NO2 over there. So overall the reaction is NO2 plus CO plus NO2 plus CO gives CO2 plus NO, right? Okay, one sec. NO plus CO2. So that's the correct reaction, the same one that's down over here. So we know that this one is correct. The next one is step 1 is the rate determining step of the reaction. Again, this is true because you have a slow reaction over here, so this is obviously true. I'm getting a call, 1 second. Yes? Dude, what? Okay. Apparently I did something wrong. Let me go see what that is. What is it? Where is it? No, I cannot hear you in the VC, Dasha. Your voice is bad. No, I'm just leaving the VC. But just tell me what I did wrong in the chat over here. Anyways, I'm going to finish this problem. So the overall reaction is this, and the step 1 is the rate determining step because that's what the slow one is. You always look at the slow part of the reaction. And then the rate expression for step 1 is rate K NO2 squared. Again, we know this is true because now we're going to look back at what the slow reaction is. So we just cover all that stuff. We see that slow reaction is 2 NO2 for the reactants. So if you're making a rate expression, it's going to be R equals to K NO2. And then you're going to square it because that's what the coefficient is at the front. So you know the rate reaction is also this. So this is correct, all 3 of these are correct, which means the answer is D. Unimethyl letter in first order, 1 second. SN1 mechanism. Okay, it doesn't matter. Like that reaction is not important at all. Like we're not going to get tested on that. It's okay. Chill. For the gas phase reaction, A gaseous plus B gaseous to C gaseous is formally determined rate expression is rate is equal to K times A times B squared. But what factor will the rate change if the concentration of A is tripled and the concentration of B is halved? So, the way that we can figure this one out is we can like literally just check what the rate's going to be. So the new rate is going to be this. We can make the changes as we like it. So the original rate R is equal to K A B squared. The new rate is equal to K. A is not A anymore, it's tripled, it's 3A. And the B is not B anymore, it's halved, it's B over 2. And that's all squared. And if you simplify this, it's going to give us 3 times 1 over 4 times K times A times B squared. If that makes sense. So the 1/2 inside over here got squared out, brought to the front, made it 1/4. The 3 over here took it out in front, made it 3. You have 3 times 1 over 4, which equals to 3 over 4, which is equal to 0.75. So the answer over here is A. What do you mean, what? It's not going to be in the test. We didn't learn SN1 mechanisms. Okay. Oh yeah, over here I don't think I can like exactly draw it because I'm on my computer, but whatever it is I can explain the answers. So hydrogen peroxide H2O2 releases oxygen gas, O2, it decomposes. I'm not going to read through everything. I don't think you could need to read through everything. Explain why the curve reaches a maximum. It's a rate of reaction. The height of bubble layer is increasing, which means there's probably more like gaseous bubbles being formed as he keeps going. Like the height just keeps going up. So that means that there's like, that shows that's a part of the rate of reaction. The reason the curve reaches a maximum is because as the reactants are converted into products, the reactants are being used up, and that slows down the rate of reaction. So that's 1 mark, so that's all you need to say. Question 2, use the graph to calculate the rate of decomposition of hydrogen peroxide at 120 seconds. The way that you would do that is to check what the tangent line is. So the reason it's 3 marks is because first you need to pop over here and draw a line there. Then you need to use a ruler to just approximate what that is, which I'm not very good at, clearly. Wait, let's see. Actually, I think I have a ruler, but I don't know if I can use a ruler. I don't know how to use a ruler. Yeah, I don't know how to use this ruler. It's fine. How do I get rid of the ruler now? What is happening? Let's go to the thing. Just get the ruler. Okay. I can draw a line like that. I can pick some point over here and some point over here. I need to find the slope between them, and that'll give me the point. That's the slope at this point. I'm not going to do that because I don't have a ruler, so I can't do it accurately, so I'm not going to like waste my time figuring that out. But that's how you do it. You have to check what the slope is. Next, the experiment was repeated using solid manganese oxide, MnO2, as a catalyst. Draw a curve on the graph to show the height of the bubble layer change over time when magnesium oxide is present. So when you have a catalyst present in the reaction, what the catalyst is doing is it's reducing the activation energy, which means that there's like more particles that are ready to start colliding once you like introduce the catalyst, which means that you're going to speed up the rate of the reaction. However, you're using the exact same amount of all the different like reactants plus the catalyst, so you're going to end up reaching the same maximum. So what's end up happening is that you're going to have a slightly steeper slope as you're going up. And that would look like is something like this. You start at the same point and you go there, it's slightly faster, and you end up at the same point. So it just has to be slightly faster, and you need to show that it's like above the thing because it's like faster than it. And it reaches the peak a little faster. Actually, let me draw that a little better. I'm show you what that looks like. Right? So, there, that's a lot better. It reaches the peak faster. That's how it looks like. Okay. Explain the effect of the catalyst on the rate of decomposition of hydrogen peroxide. The catalyst reduces the activation energy of the reaction, which allows more like high energy particles to basically collide. Don't quote me on that. I'm not amazing at these. I'm more amazing. I'm okay at the math. I'm not like perfect at this, but generally the effect of the catalyst is to reduce the activation energy for the decomposition of hydrogen peroxide, which increases the rate of reaction. Okay, nitrogen dioxide and carbon monoxide react according to the following equation. Experimental data shows since the reaction is second order with NO2 and zero order with CO, state the rate expression for this reaction. And this should be, because you know that it's the form of rate reaction is always R equals to K first. Then let's look at the first reactant, NO2. And we're being told it is second order, which means it's going to be squared. And then the other reactant is CO. What do I know? The other reactant is CO, and we know that that is zero order with respect to CO. So it's zero, which means it cancels out. You don't even need it. So it's just this. This is your rate expression for that one. Then the one below it, the following mechanism proposed to the reaction, identify the rate determining step, giving your reason. So the rate determining step is always the one that has the same rate expression as the overall reaction. So we just need to figure out which one of these is the rate determining step by figuring out which one of these has the same rate expression as the one we found right above. So for step one, the rate expression, if you look at, that's one of the reactants, that's the other reactant, they're both the same, but let's treat them as two different ones. R is equal to K, NO2, NO2, as so, but that simplifies into K NO2 squared. So that's actually the same thing as over here. So we already know that step one is rate determining step. However, we can again just show the other one doesn't work, because the other one is K NO3 CO, which doesn't work either. So it doesn't work. So it's not this. It's going to be step one as your rate determining step. And the reason is that it has the same rate expression as the overall reaction. Any other things said? Okay. So the Arrhenius equation, K equals to A e to the power of negative activation energy over RT. Here's the relationship between the rate constant and temperature. So the rate constant is, let me just write again. The rate constant is K, and the temperature is over here, T. And the activation energy is here, EA. The relation to temperature affects energy, activation energy. There is no relationship. So the temperature does not affect the activation energy. And an easy way to look at that is just look at the equation itself. K is equal to A e to the negative EA over RT. R is constant. R is constant. We know that temperature cannot affect the activation energy. Because temperature, if you look at the Boltzmann curve, the temperature changes the Boltzmann curve itself, but it doesn't change the activation energy, because the only thing that can change the activation energy is the catalyst. So the temperature changes, and then the rate constant changes alongside the temperature. So the temperature and the rate constant change together. However, the activation energy is not changed at all. It stays constant for any given reaction. So for any given reaction, the activation energy has to be the same, unless you add a catalyst and you change the reaction pathways themselves. So it doesn't actually go through the reaction the same way, it will go through a much faster way. So yeah, that's why that works. Okay. Cool. So chemical kinetics involves understanding how the molecular world changes with time. Define the rate of reaction. So the rate of reaction is the speed at which the products in a reaction, the reactants in a reaction are converted into products. Next one. So temperature and the addition of a catalyst are two factors that affect the rate of reaction. State two other factors. So there's a couple of factors you can see over here. One, it could be you could increase the pressure or decrease the volume. The pressure and volume are connected, so those are one reason. You could increase the surface area of the reactants, and you could also increase the concentration of the reactants. So those are three reasons. So you could have pressure volume, you could have the surface area of the reactants, or you could have concentration of reactants. There might be more, but those are the ones that I thought of. Interaction representative, state one method that can be used to measure the rate of reaction. Okay, so one thing that you could notice over here, I'm not too sure if this is the best way, because like there's this is what is it? This is from topic 8 maybe, acids and bases, but essentially when you have more hydrogen ions, like the H pluses, you're actually reducing the pH. So the more like H plus you have, the more of these that you have, you're making it more acidic. And that's like the general rule. So the more of this you have, the more acidic it is. So if you notice, you have a lot of hydrogen ions on the left, and you have none on the right, which means that as the reaction continues happening, all this acidic substance over here on the left gets converted into a neutral substance on the right over here, which means that eventually the substance is going to become more and more basic. So pH is a good method of showing the rate of reaction here. So yeah, you can use like a pH like thing, like, you know, the things, yeah, with like an indicator or something. So for the reaction below, consider the following experimental data. Okay, I'm just gonna zoom in a little bit. I'll do the math for this one. Is there anything here? Whizzing, observing the increase in Cl2. No, so you can't say observing the, so Dasha asked if you can, like, absorbing the increase in Cl2 aqueous count. The reason that doesn't count is because there's no way to check whether Cl2 aqueous is increasing. If it was a gas, it would be okay, because you would have chlorine gas coming out of it, which means you could measure with a gas syringe. However, no, it's aqueous and it's dissolved into the water, so it's invisible and you can't see it. So yeah, that's the answer to your question. Okay, I'll do the math for this one. Just gonna play around with this and see how this works. View actual size. Yeah, okay. So let me, okay, there. Okay, so, let's look at this. The rate expression. So we need to look at, so we have the rate expression, the generic rate expression is going to be ClO2, and it's going to be to some power x, and it's going to be OH minus, and it's going to be some power y. And we need to find out what those are. So the order, so the way we can do that is by looking at what happens when we increase or change something about this reaction. So let's look at from experiment 1 to experiment 2. You have from let me go from experiment 2 to experiment 1. I think that's a little easier. So you're going from experiment 2 to experiment 1. What ends up happening is you have over here 0.05 molarity, and over here you have 0.1. So what you're doing is that you're doubling your molarity. So this is a times 2 to go up, and then over here, if you can see, what ends up happening is that in order to get from 5.75 times 10 to the negative 2 to 2.3 times 10 to the negative 1, the way you can check that, you can divide 2.3 times 10 to the negative 1 by 5.75 times 10 to the negative 2, which allows you to see that it is an increase of times 4, so it's times 4. So that means that if you double the concentration of ClO2, you are going to quadruple the reaction rate, which means that the order of this reaction is 2, because if you double the ClO2 concentration, it's gonna go times by 4 because of the square. Now for OH minus, what ends up, you can then analyze reactions 2 and 3, and going from reaction 3 to 2. So what ends up happening when you're going from 3 times 10 to the negative 2 to 1 times 10 to the negative 1, you're going approximately 3.3, continuing 3 forever, like 3.3333. That's how fast your reaction is increasing. That's how much the concentration is increasing. But if you look at the reaction increase, this again, if you need to like prove this and show it, but again, it's approximately 3.33, like it's around there, which means that it's going to have order 1, which means that like if you increase the concentration of OH by 3, you're going to increase the rate of reaction by approximately 3. That's 1. So that's what the rate expression is going to look like. Now determine the rate constant K and state its units using the data from experiment 2. So the way that you would do this one is that you would take any arbitrary, I'll just restart it, wait. So determine the rate constant. So the way I would do that is that I can look at our equation again. So our K ClO2 squared and OH minus, and now what I can do is I can plug in. So I'm going to look at experiment 1. I'm going to plug in the initial rate over here. I'm going to make it 2.3 times 10 to the negative 1. Okay, I'm going to make it 2.3 times 10 to the negative 1, and I'm going to remember, actually, this is a bit annoying. I'm not going to do this here because there's too much like stuff and it's not enough space. Wait, I'm going to copy this over to the whiteboard. Wait, if I zoom out, you should be able to get the entire thing. Anything here? Okay, so here it is. The rate constant, okay, so I know that my equation is R is equal to K ClO2 squared OH minus to the power of 1. Now what I do is that I can substitute in everything I need to substitute in. So I can I'll just use all the data from experiment 1. So the initial rate is equal to 2.3 times 10 to the negative 1 moles per mole dm. I'm not going to use the entire thing, I'm just going to use m instead because it gets a little confusing. So m s to the negative 1 is equal to k times ClO2, which is going to be the initial CO2 concentration is 1 times 10 to the negative 1. So I'm just going to keep that 10 to the negative 1 mole m squared, and then this is times the OH concentration, which is at this stage going to be 10 to the negative 1 again. That's 10 to the negative 1 concentration to the power of 1. If I set to solve for k by taking all of these concentration stuff over here, putting it to the other side by dividing it through by them, I'll get 2.3 times 10 to the negative 1 moles per second over 10 to the negative 1 moles times 10 to the negative 1 squared, which is 10 to the negative 2 moles squared. So the moles cancel out, the 10 to the negative 1s cancel out over here, and what you're left with is 2.3 times 10 to the 2 moles negative m over m negative 2 s negative 1. So the m squared over here, I put it up to the top, I make it m to the negative 2, and the 10 to the negative 2 over here, I put it up top, made it 10 to the power of 2, and then this ends up with 230 m to the negative 2, s to the negative 1. If you were to write this m in full form, what this would look like would be 10 squared, m is mole per dm cubed, it's mole squared, dm negative 6, s to the negative 1. That's what the full form looks like, but I assume this is fine. Last one, calculate the rate in mole dm cubed when ClO2 aqueous is that, and that is that. Okay, so now you know you're given two concentrations and you want to figure out what the rate is going to be. The way that you would do that is you would look at you would use your rate constant over here and your rate expression over here to figure it out. So what you do is you want to find the rate of reaction, R is equal to K times the concentration of ClO2 squared times OH. So that's 2.3 times 10 squared m negative 2 s negative 1 times ClO2 squared. So that's going to be what is over here, 1.5 times 10 to the negative 2 m squared. One second, I'm going to move this over, so I'm going to lasso this. Okay. Oh, I didn't lasso it correctly. That's stupid. There. I'm gonna move that here. And let's continue. So that's the ClO2 concentration squared times the OH concentration, which is 2.35 times 10 to the negative 2 m. The m to the negative 2 cancels out with the m inside here, because what you have is an m squared. So this I can cancel this out, and I can cancel out the m negative 2 over here. I'm just doing that right now. So now I have 2.3 times 10 squared times 1.5 times 10 to the negative 2 all squared times 2.55 times 10 to the negative 2 m. And also I forgot the s to negative 1 from over there, so I'm putting the s negative 1 over here. Note, now you know your units are correct because the rate of reaction is molarity per second. So you have all of these numbers and then molarity per second. So you know that your units are right, that means you know your rate constant's right, and you know your entire rate expression is correct. So now we can plug in the numbers, and I think the answer is, if I'm correct, this cancels with this as well, 10 squared times 10 to the negative 2. So it's going to be a number. And I don't know what that number is because did I do this? I mean I did, but where did I do this? It's okay. I think you guys can calculate this. I'm not going to calculate this. Calculate it, and you'll get the answer. It's fine. Okay, describe qualitatively the relationship between the rate constant K and temperature T. Qualitatively speaking, as the temperature T increases, the rate constant K also increases. And the way that we know this is by looking at our Arrhenius equation again. So let's have a little look-see. Wait, make it white and right over here. So A is equal to, no, it's not A. Sorry. It's K is equal to A e to the negative EA over R temperature. So if you look again at what this is, it says A, and e to the negative something is going to be 1 over e to the activation energy over RT. Now, if you look at everything that's happening over here, if you increase the temperature in the bottom over here, so if you increase the temperature over here, in the fractional exponent over here, the entire denominator is going to get smaller. And as the denominator gets smaller, as you increase the temperature over here, as this denominator gets smaller, this entire fraction over here is going to get larger, because as the denominator gets smaller, the entire fraction gets larger. So everything gets larger, which means that the rate constant increases. So as the temperature increases, the rate constant increases. And you can see this from the Arrhenius equation very easily. And that's qualitatively what the relationship is. Okay, two-step mechanism is proposed for the following solution. Deduce the overall equation for the reaction. The way that you can do this is you could, all you have to do is cancel out the correct stuff. Why did it go here? Overall reaction equation, ClO2 minus and ClO2 minus over there, so I can remove that. Oh wait, there's the color back. There, that. And now you have ClO minus and ClO minus, so that's 2 I can write it over there. That's 2 ClO minus plus another ClO minus over there from the reactant side of it. So I'm going to make it a 3. So if that's taken care of all the reactants over here, now all the products you're going to have, it's going to become ClO3 minus plus 2Cl minus, like that. And that's the overall reaction over here. Okay, don't forget the units things, the aqueous stuff like that. That could be important, so don't forget that. But I forgot it over here, but don't forget that. And yeah, that's what the overall reaction is. It's already balanced because it should be balanced, because you have two mechanisms that when you add them together, everything always stays balanced. Deduce the rate expression for each step. This thing is the last question, actually. Yeah, probably the last question of the test. The rate expression for each test step. Wow, I'm really stupid. I moved the equation out there. There. Okay, so for step number 1, you're looking at the reactants. So you're going to end up with R is equal to K times the reactants, ClO minus, and another ClO minus, which if you combine them is equal to K ClO minus squared. If you look at for step 2, that's equals to R is equal to K ClO2 minus ClO minus, and that's your rate expression for the other one. Looking at reactants, and this is the one for the first one. And those are your marks, 2 marks. That's it. That's the entire paper. 0.001216. Thank you very much, Dasha. I am finishing the session. Bye-bye.